Hey guys, this is Charumathi from second year BTech IT. Here I am going to discuss about 8086 microprocessor. Here we are going to see the introduction about microprocessor, definition of microprocessor, features of 8086 microprocessor, and finally the architecture of 8086 microprocessor. So let's get started with the introduction. 8086 microprocessor is an enhanced version of 8085 microprocessor that was designed by Intel in 1976. It is a 16-bit microprocessor having 20 address lines and 16 data lines that provides up to 1 MB storage. It consists of powerful instruction set which provides operations like multiplication and division easily. It supports two modes of operation, that is maximum mode and minimum mode. Maximum mode is suitable for system having multiple processors and minimum mode is suitable for system having single processor. Definition for microprocessor. A microprocessor is an integrated circuit which incorporates core function of a computer's central processing unit CPU. It is a programmable multi-purpose silicon chip, clock driven, register based, accepts binary data as input and provides output after processing it as per the instructions stored in the memory. So let me show you the block diagram for microprocessor. Here the microprocessor is placed between the input and output device where it acts as the intermediate between input and output. Here some of the examples are Intel 4004, which is known as the first microprocessor, then Intel 8085, Intel 8086, Intel Pentium 4, Intel Core i7, AMD Athlon. Then the features of microprocessor. The most prominent features of a 8086 microprocessor are as follows. It has an instruction queue which is capable of storing 6 instruction bytes from the memory, resulting in faster processing. It was the first 16-bit processor having 16-bit ALU, which is known as arithmetic logic unit, 16-bit registers, internal data bus and 16-bit external data bus, resulting in faster processing. It uses two stages of pipelining, that is fetch stage and execute stage, which improves performance. Fetch stage can prefetch up to 6 bytes of instructions and store them in the queue. It consists of 29,000 transistors. Then the architecture of 8086 microprocessor. The internal architecture of Intel 8086 is divided into two units, the bus interface unit and the execution unit. These are explained as following below. So then the architecture of 8086. This is the block diagram of 8086 where bus interface unit fetches instructions, reads data from memory and I/O ports, writes data to memory and I/O ports. Whereas in execution unit executes instructions that have already been fetched by the bus interface unit. BIU and EU functions separately. Let me tell you the function of these block diagram. BIU. In this BIU, the address generation is to dedicated added to generate 20-bit address. It consists of four 16-bit segment registers, namely code segment, data segment, stack segment, and extra segment. IQ, which is known as instruction queue. BIU contains the IQ, a group of first in first out, which is we are shortly known as FIFO, in which up to 6 bytes of instruction codes are pre-fetched from the memory ahead of time. This is done in order to speed up the execution by overlapping instruction fetch with execution. This mechanism is known as pipelining. Code segment register. It is a 16-bit register. It is used for addressing a memory location in the code segment of the memory where the executable program is stored, which is CS contains the base or start of the current code segment. IP contains IP, which is known as instruction pointer. IP contains the distance or offset from this address to the next instruction byte to be fetched. BIU computes the 20-bit physical address by logically shifting the contents of CS 4 bits to the left and then adding the 16-bit contents of IP. That is, all instructions of program are relative to the contents of the CS register multiplied by 16 and then offset is added provided by the IP. Next one is data segment register. Same, it is a 16-bit register. It consists of data used by the program accessed in the data segment by the offset address or the contents of other register that holds the offset address, which means it points to the address data segment. Operands for most instructions are fetched from this segment. The 16-bit contents of the source index, which is SI, or destination index is DI, or a 16-bit displacement are used as offset for computing the 20-bit physical address. Next one is stack segment register. Same, it is also a 16-bit register. It points to the current stack. The 20-bit physical stack address is calculated from the stack segment and the stack pointer for stack instructions such as push and pop. In based addressing mode, the 20-bit physical stack address is calculated from the stack segment and the base pointer. It handles memory to store data and addresses during the execution. Next one is extra segment register. It is also a 16-bit register, points to an extra segment in which data is stored. String instructions use the ES and DI to determine the 20-bit physical address for the destination. ES is an additional data segment which is used by the string to hold the extra destinational data. Next one is an instruction pointer. It is also a 16-bit register. It always points to the next instruction to be executed within the currently executing code segment. So this register contains the 16-bit offset address pointing to the next instruction code within the 64 KB of the code segment area. Its content is automatically incremented as the execution of the next instruction takes place. Next one is the execution unit. Execution unit gives instruction to BIU stating from where to fetch the data, and then decode and execute those instructions. Its function is to control operations on data using the instruction decoder and ALU. EU has no direct connection with system buses as shown in the diagram. It performs operation over data through BIU. ALU is an 16-bit register performing arithmetic and logic operations like addition, multiplication, subtraction and division, or and not operations. Accumulator register. It consists of two 8-bit registers AL and AH, which can be combined together and used as a 16-bit register AX. AL in the case contains the lower order byte of the word and the AH contains the high order byte. The IO instructions use the AX or AL for inputting and outputting 16 or 8-bit data to or from an IO ports. Multiplication and division instruction also use the AX or AL. Base register. It consists of two 8-bit registers BL and BH, which can be combined together and used as a 16-bit register BX. BL in the case contains the low order byte of the word and BH contains the high order byte. This is the only general purpose register whose contents can be used for addressing the 8086 memory. All memory references utilizing this register content for addressing use DS as the default segment register. Counter register consists of 2-bit registers CL and CH, which can be combined together and used as 16-bit registers CX, which combined CL register contains the low order byte of the word and CH contains the high order byte. Instructions such as shift, rotate and loop use the contents of CX as a counter. Data register. It consists of two 8-bit registers DL and DH, which can be combined together and used as a 16-bit register DX. When combined, DL register contains the low order byte of the word and DH contains the high order byte, used to hold the high 16-bit value in 16 into 16 multiplication or the high 16-bit dividend before 32 divided by 16 divisions and the 16-bit remainder after division. Stack pointer and base pointer. SP and BP are used to access data in the stack segment. Stack pointer is used as an offset from the current SS during execution instructions that involve the stack segment in the external memory. Stack pointer contents are automatically updated, which is incremented or decremented due to the execution of a pop or push instructions, whereas base pointer contains an offset address in the current stack segment, which is used by instruction utilizing the based addressing mode. Source index and destination index. It is used in indexed addressing. Instructions that process data strings use the SI and DI registers together with DS and ES respectively in order to distinguish between the source and destination addresses. Flag registers. It has 9 flags that help change or recognize the state of the microprocessor. It has 6 status flags. Number 1. Carry flag. This flag is set when there is a carry out of MSB in case of addition or a borrow in the case of subtraction. Number 2. Party flag. This flag is set to 1 if the lower byte of the result contains even number of ones for odd number of ones set to 0. Number 3. Auxiliary carry flag. This is set if there is a carry from the lowest nibble, that is bit 3 during addition, or borrow for the lowest nibble, that is bit 3 during subtraction. Number 4. Zero flag. This flag is set if the result of the computation or comparison performed by an instruction is 0. Then sign flag. This flag is set when the result of any computation is negative. Then overflow flag. This flag is set if an overflow occurs, that is, if the result of the signed operation is large enough to accommodate in the destination register, the result is of more than 7 bits in size in case of 8-bit signed operations and more than 16 bits in size in case of 16-bit signed operations, then the overflow will be set. Status flags are updated after every arithmetic and logic operations. Then it also has 3 control flags, namely trap flag, interrupt flag, direction flag. Number 1. Trap flag. If the flag is set, the processor enters the single step execution mode by generating internal interrupts after the execution of each instructions. Number 2. Interrupt flag. It causes the 8086 to recognize external mask interrupts, clearing if disables these interrupts. Number 3. Direction flag. This is used by string manipulation instruction. If the flag bit is 0, the string is processed being from the lowest address to the highest address. That is auto-incrementing mode. Otherwise, the string is processed from the highest address towards the lowest address. That is auto-incrementing mode. The control flags are used to control certain operations. 8086 registers categorized into 4 groups, which is known as general purpose registers, pointer registers, index registers, instruction pointers, segment registers, and flags. Then here I have mentioned some of the special functions of registers. Register AX is an 16-bit accumulator. It stores the 16-bit results of arithmetic and logic operation. AL. It is an 8-bit accumulator. It stores the 8-bit results of arithmetic and logic operation. BX. Base register. It is used to hold base value in the base addressing mode to access memory data. CX. Count register. It is used to hold the count value in shift, rotate, and loop instruction. DX. Data register. It is used to hold data for multiplication and division operation. SP. Stack pointer. It is used to hold the offset address of top stack memory. BP. Base pointer. It is used to hold the base value in base addressing using SS register to access data from the stack memory. SI. Source index. It is used to hold index value of source operand for string instruction. DI. Data index. It is used to hold the index value of destination operand for string operations. Hope you all enjoyed this. Thank you.